All right, welcome Perspectives, and it's my pleasure to introduce you to Dr. Luke McGuire. Dr. McGuire is a geomorphologist who has interest in sediment transport on individual storm levels, but also over millions of years and how it influences landscape evolution. Dr. McGuire is a mathematician. Originally at Bucknell, he majored in math. He then moved on to the University of Arizona, where he was a master's student in applied math and then a PhD student in applied math. And then he transitioned as a postdoc. He earned a Mendenhall postdoctoral fellowship with the USGS and was located in the landslide lab in Golden, Colorado. After that, University of Arizona rehired him. But at a significant salary bump, I assume, where he's now a professor in the Department of Geosciences. And today he's going to talk about wildfires and debris flows in wildfire burn scars. So welcome.
Thanks. Thank you so much for that introduction, and thank you for the invite to be here. It's really, really exciting, and I'm looking forward to meeting with you all throughout the day. So yeah, I just kind of want to get things started today, talking about a little bit of the background or setting the stage for this problem of why we want to understand what happens after the flames are out, after a fire happens. How does the landscape respond in terms of flooding and debris flows? Well, what's going on right now in the Western US and more broadly throughout many areas in the world is that we're seeing extremely large increases in the area that's being burned. Here's a graph showing area burned in the Western US from 1984 through 2020. Down here, this is specific to Arizona and New Mexico because there are regional differences throughout the Western US, but we see this trend in a number of places of also increasing severity of these fires. So we're getting more frequent fires, they're becoming larger, they're becoming more severe. And as that happens, there are a lot of implications for water-related hazards and management issues in terms of reservoir sedimentation, water quality, because the effect of all of this increasing fire activity is that we're right now already seeing increased sediment yields from a lot of watersheds in the Western US, and those increased sediment yields are projected to continue and become exacerbated in the future. This was one modeling study that looked at changes in sediment yields associated with fire-related erosion between 2000 and 2010 versus 2041 to 2050. And they projected in more than 90% of watersheds that they looked at least a 10% increase in sediment yield. So this poses a lot of issues for people that are charged with managing land and water resources. There's debris flow and flash flood in the title. It's maybe a bit of false advertising. I wasn't sure initially how much I would focus on one or the other, but I can tell you now I'm going to focus mostly on debris flows, although a lot of what I have to say is also relevant for flash flood hazards. But since there's a focus on debris flows, I wanted to just be upfront about what I mean when I say debris flow so that you all have a picture of that in your mind. And when I talk about debris flows, I'm using the term very generally to refer to something that's a mixture of water, mud, rocks, trees, other organic debris, and they tend to have extremely high sediment concentrations, so 40 to 50% at least, and that's what separates them from flood-dominated flows, water-dominated flows and floods that have much less sediment concentration. And as a result of this increase in sediment, the physics of how these flows move is quite different. And one of the major implications of that is that these debris flows tend to develop really coarse-grained, deep flow fronts. And you can see that in this image here of all of these boulders that have moved up to the front of the flow. The largest particles in these flows tend to migrate out to the front and to the lateral edges. And that means that these flows are much more likely to avulse out of channels and potentially impact people and infrastructure versus flood flows that don't develop these types of coarse-grained flow fronts. You can see here some of the devastating impacts of flow interacting with infrastructure down there. Here's some more images just to bring home the hazards implications of trying to understand these flows. And in particular, I'm going to focus on today, or one thing I'll focus on is trying to differentiate the types of rainstorms that lead to flood responses versus debris flow responses, since they are so different. We want to know when we're going to get one versus the other in order to anticipate and mitigate the effects of these flows. In addition to directly impacting infrastructure, debris flows can indirectly impact local economies in a number of ways. And one of them is by damaging and closing major highways. This is I-70, a major highway in the Colorado Front Range that a number of people rely on, and it was shut down for a period of more than a few days after the Grizzly Creek fire. This is a photo from Glenwood Canyon of a large debris flow that covered this highway and meters of mud and sediment. The debris flows after this fire also partially dammed the Colorado River, almost completely damming it. And so even if you're not interested or motivated by the direct hazards posed by debris flows, they move a substantial amount of sediment. And all of that sediment, once it's mobilized and dumped into the larger channel network, eventually works its way downstream. So this has implications, as I mentioned before, for water quality and reservoir sedimentation and things of that nature. And if that doesn't grab your attention, if you're more interested in longer timescale processes, disturbance, especially associated with fire, matters on these timescales too, because the erosion that happens after fire may actually account for a fairly large percentage of long-term denudation rates. This is a study from the Valle Caldera in northern New Mexico by John Pelletier and Caitlin Oram, and they looked at the impacts of fire on erosion rates and found that in the years immediately after fire, short-term erosion rates measured from sediment concentration, I think these are mostly from sediment concentrations in stream sediment or stream flow, that these were extremely elevated, orders of magnitude higher than what you would typically get in like background erosion rate estimates from non-fire affected years. And if you correctly do some weighted averaging of these two short-term erosion rates based on the frequency of fire, then you can recover the long-term denudation rates pretty well. But if you don't account for the elevated erosion in these fire affected years, then you're not going to correctly predict the long-term sediment budget. Okay, so for all of these reasons, I'm particularly interested in fire and also in these extreme events, these debris flow events that tend to mobilize a lot of sediment compared to kind of the more mundane flood flows. And one of the most recent examples highlighting the hazards of these associated with these events happened after the 2017 Thomas Fire, which burned a large area near Montecito, California. Here you can see a dot roughly where that is, where the Thomas Fire burned. And this is a small section of that very large fire, and it was impacted by a relatively weak atmospheric river, actually, that had within it a fairly intense band of precipitation. And that band moved over this part of the burn area and triggered a number of debris flows in these recently burned watersheds that then moved downstream across a populated alluvial fan and destroyed a number of houses, injured a number of people, and led to tens of fatalities. And so this is really the motivation for me for wanting to improve our ability to assess and mitigate the impacts of these flows. And that involves a number of different puzzle pieces here to put this all together. Thinking about what watersheds might be susceptible to these types of extreme responses, we have to consider topography and in general geologic setting. How steep is the terrain? What type of sediment is available there to be transported? What's the typical rainfall intensity that this area receives? Over what duration does rainfall typically occur? What are the burn severity characteristics of a fire that we're interested in? Is it a moderate to high severity fire that completely incinerates all of the canopy and the vegetation and has really large effects on the soil? Or is it a relatively low severity fire that doesn't kill a lot of the vegetation? And then if we really want to get into quantifying risk and in a serious way, we'd have to consider what is actually downstream. Is it a populated area? What type of infrastructure is there? What types of values might those flows impact? And I won't really talk about this piece of the puzzle at all, but I'll at least hit on these other three. And I'm going to kind of break this down into three really basic questions. How likely is it that an area will produce a debris flow after a fire. And when I talk about this, I'm really thinking about a spatial scale associated with a small watershed. So maybe 1 square kilometer up to no more than 10 square kilometers. So here's an example of what these watersheds might look like. You see the scale bar up here, 4 kilometers. So these are fairly, our spatial scale today is fairly limited. And so within a burn scar, there might be thousands of these types of watersheds. But we want to get down to this level of granularity because that's particularly helpful for a lot of people who need to make decisions about where they might want to put mitigation measures in place, for example, or where they may want to issue evacuation orders and things like this. So not only how likely is a debris flow going to be in each of these different kind of watersheds that we're thinking about, but how big is the debris flow going to be when it occurs? And then where will those flows go? What areas might they impact downstream? Regardless of whether or not you're interested in kind of looking at long-term sediment budgets or hazards on the scale of one rainfall event, these are questions that you probably need to know the answers to. So for today, I'm going to start by talking about debris flow initiation in burned areas to get at this question about how likely debris flows are. And then I'll talk in sequence about these other 2 questions. How big are they and how far will they go? And I'm going to mention a number of different methods that we tend to use to try to answer these questions. And our general strategy involves a combination of making observations and measurements in burned areas, using those observations and measurements to train data-driven or empirical models, and using those measurements and observations to help us constrain physics-based models. And I think all of these things then in turn inform each other. We learn more about the processes that we're trying to study from both of these models, and we use them to iteratively improve. And then based on what we find out from the models, we tweak our techniques for what observations we make in burned areas and what measurements we make. And so we've developed over the last 7 or so years that I've been at the University of Arizona, a large network of post-fire hydrologic monitoring sites where we make these observations and measurements. And that's in collaboration with a lot of folks at the Arizona Geological Survey and the US Geological Survey, and a lot of my former and current graduate students and postdocs. So a lot of what I'm going to talk about today is a hodgepodge of various projects that all of these folks have been involved with. Okay, so starting with this first question, how likely are debris flows to be after a fire? I wanted to give a brief overview of what we know about the impacts of fire on the landscape. A lot of that can be summarized by looking at this image here. This is one case where some fire retardant did a nice job, and what looks like a hand line that a crew made here on this ridge. A nice job of stopping the fire. So that's why all the vegetation here is red, is it's fire retardant. This area, this slope in the San Gabriel Mountains in Southern California, extremely steep. It all burned at moderate to high severity, and you can see that there's no vegetation. There's very little of any canopy left. This is 2 months after the fire. This is what the canopy looks like and the vegetation density before the fire. So the result of this loss of canopy is that there's no longer any interception. There's no rainfall interception. So in an unburned setting like this, as it rains, that canopy can actually store a decent amount of rainfall, and some of that will get evaporated back into the atmosphere, and it won't contribute to runoff that might produce floods or debris flows or move lots of sediment. There's also no water storage in any litter or duff or that dead and decaying organic matter that you often see on an unburned forest floor, because that's all gone now. And not only do you lose that water storage capacity, but you also get a surface that's extremely low roughness. And as a result of that, water moves faster. So surface water flow velocities are much higher, and water concentrates more efficiently down into channels. There's also one commonly cited effect of moderate high severity fire is that the soils become water repellent. This doesn't always happen, and actually unburned soils are themselves often very water repellent, but fire tends to enhance that. And I'll show a video of that in just a second, illustrating the effects of this water repellent layer if and when it forms. And all of these effects, though, I'd like to mention are transient, and I'll hit on this a little bit later, but they obviously don't last for forever. The landscape will recover, the soils and vegetation will recover. And you can see after 3 years here that the vegetation density certainly isn't back to what it was pre-fire, but it's on its way. So here's a video of me doing a not very scientific experiment to assess the severity of water repellency after a fire in Southern California. This is the San Gabriel Mountains right outside of Los Angeles. I'm just taking some water from my water bottle and squirting it on the ground. I've kind of moved aside the ash, which is the black stuff, to get down to the mineral soil. It was a windy day, so you'll see this blob of water kind of oscillate a little bit as the wind blows it around, but it's not infiltrating into the soil. That's not typical. And so this is one of the this is kind of a fairly extreme example. It's like putting a giant raincoat on the landscape or turning it into a parking lot effectively when it comes to changing infiltration capacity. So all of these things lead to orders of magnitude increases in runoff and subsequently in erosion. One effect of that is an increased likelihood of seeing debris flows, which in immediate post-fire settings tend to form when you get water concentrating in gullies and low order channels and steep hill slopes and rapidly mobilizing a substantial amount of sediment. And through that process, they transition from these water dominated flows that act like Newtonian fluids to these debris flows that act quite differently. And they carry very large boulders in suspension, and that can lead to really large impact forces on objects that they may encounter downstream. And I want to emphasize also that all of this is happening at very small drainage areas. So we're talking about these debris flows initiating maybe less than 100 meters off of these upper cliffs here. So this is where these debris flows initially get started. If we want to look at initiation, we have to consider what's going on at kind of these fairly small scales. This is an example of a post-fire debris flow getting started. This is photos from a time-lapse camera. This is a fire in western New Mexico, and the camera was set up to take pictures every minute. So you'll see fairly quickly, it starts to rain, and then fairly quickly we get runoff. Fairly quickly we get more runoff, and it's obviously really hard to see, but when you look at the deposits downstream of this site, this is a watershed that's the size of just a couple of football fields, and so it responds very rapidly to this short duration, high intensity burst of rainfall and produces a debris flow. It starts out with just a trickle of runoff, and then it very quickly escalates above that. And so this is the type of threshold behavior that we tend to see in these systems. There's some threshold of rainfall intensity that's reached, or equivalently some threshold in the amount of runoff that we're getting. And then at that point, things rapidly accelerate and change, and the flow is capable of picking up a lot more sediment a lot faster, and it produces these debris flows. So a natural question is, well, what is exactly the threshold for debris flow initiation in these landscapes? Can we quantify it more precisely? And small scale experiments and a limited number of field studies had suggested that there's a quantity called dimensionless discharge that might be useful for delineating a threshold from more of a water dominated flow to a really high sediment concentration debris flow. And this dimensionless discharge quantity is shown in all its glory up here. We don't need to get into the details, but one of the key quantities is what's called a unit discharge, which you can think of as the velocity of a flow times its depth. So if you have a flow that's moving faster or a flow that's deeper, you have a higher dimensionless discharge. And in the denominator here is a median grain size. So if you have really coarse sediment sitting in the channel, then you would have a high median grain size, and you would need a faster moving flow or a deeper flow in order to get a higher value of dimensionless discharge. So larger grains means lower dimensionless discharge, smaller grains means higher dimensionless discharge, greater flow means higher dimensionless discharge. And for a given slope, there's some critical value of dimensionless discharge shown here by these lines, depending on which study you look at, that would delineate whether or not you would get a debris flow in response to some amount of runoff. So as your landscape gets steeper, it takes less dimensionless discharge, or equivalently slower moving flow or less deep flow, to produce a debris flow. But if you have a landscape that's not particularly steep, then you may need quite a bit more. runoff discharge in order to produce your debris flow. And so we set out to see whether or not this would actually work for the scales we were interested in, watershed scale problems, assessing what's the likelihood that we might get a debris flow in response to a particular rainstorm in some 1 square kilometer or 3 square kilometer watershed. So we monitored this watershed, roughly 1 square kilometer in Southern California. We had rain gauges installed at the upper and lower ends of the watershed. We had cameras at the lower end and some other equipment to monitor hydrologic response. This is a screen capture from one of the videos that we got from a debris flow on January 20th, 2017. And from all this equipment, we were able to pinpoint pretty precisely down to really the second when debris flows were passing by our monitoring station at the outlet. And we could use the information that we collected at this site, in situ measurements of infiltration capacity of the soil, combined with rainfall observations, combined with some calibrations we were able to do based on data we had at this lower monitoring station. We were able to constrain a hydrologic model and then use that hydrologic model to predict what the dimensionless discharge was throughout this watershed at the time when these debris flows were initiated. And then we could look at that dimensionless discharge as a function of slope for times when debris flows were initiating and times when debris flows were not initiating, or in other words, when we were getting flood flow responses or relatively little response. And then you can envision, as we did here, putting a line through this. There's some gaps in the data, so of course there's some uncertainty here for sure. But we were able to delineate a threshold that pretty well separated dimensionless discharges associated with floods from those associated with debris flows. And then we can use this dimensionless discharge threshold in combination with a hydrologic model at other sites to try to understand what type of rainfall or runoff response it might take to transition into a debris flow. Yeah.
Just quick clarification, the slope, does it enter or where does it enter? This dimensionless discharge?
Slope doesn't directly enter the dimensionless discharge equation. It's just the critical amount of dimensionless discharge that you need to produce a debris flow is a function of slope. Yeah. Yeah, and slope kind of indirectly enters this in that the slope will affect the velocity and depth of the flow. Yeah. Okay, so here's our threshold shown more plainly without all of the data. And you could envision that for a given slope, we could run a hydrologic for a given slope in a given rainstorm. We could run the model and decide whether or not, or just look at the model output and see whether or not the predicted discharge falls above or below this line, and then say whether or not we thought debris flows were likely to initiate at that location. One of the challenges with that is you need to have the data to be able to constrain your hydrologic model. And if you've never even thought about a hydrologic model in your life and what might go into this, you could probably intuit that there's got to be something that tells you in a rainstorm, if we were given some rainfall intensity, we need to know how much water is infiltrating into the soil. And this is challenging after a fire because fire affects the soil properties. So we can throw out the window all the things that we thought we knew about what affects infiltration rates in unburned soil, because the burned soils we know they're going to be different. So even though general rules may exist about like, oh, given this soil texture, we expect that saturated hydraulic conductivity and these other variables that control infiltration rates will be X. Well, in a fire affected area, it's no longer X anymore, partly because of some of those water repellency effects that I mentioned. It's usually X over 3 or X over 4. It's much lower. So more of your rainfall gets converted into runoff. But we can make some measurements out in the field to try to constrain that. And maybe we even have some data that we can use to validate the results of using these measured values. There's some parameter, we usually use a Manning coefficient. It's related to the roughness of the surface, which I mentioned earlier. The fire changes by generally making things smoother and incinerating a lot of that litter and duff that kind of slows down runoff on the forest floor. In this dimensionless discharge, there's also a grain size. So you want to have some constraints on the median grain size of material in the channel that the debris flows are eroding through. If it's finer, it's easier for those debris flows to start. If it's coarser, it's harder for them to get started. And given all this information in some rainstorm, you could produce a map of the peak dimensionless discharge throughout your watershed, and based on the slope and how it varies throughout the watershed, you could compare these values with that threshold curve and make some decision about debris flow potential in this watershed. And one of the things that this allows us to do is to make predictions or assessments of potential debris flow activity in areas where we don't have a lot of historical information. Fires are starting to burn in areas where we don't have any observations in the past because maybe the climatic conditions were such that that area just wasn't fire prone, but it is now. So people are looking for answers and saying, well, this area's never burned before. Do you think we're going to have debris flows here? And in Southern California, you can somewhat answer that question by just saying, well, look at what's happened historically. We've gotten fires here every 20 years for the last 100 years, and people kind of know what's going to happen to a certain extent. There's large portions of the Western US where we can't really say that. One of them is the Sonoran Desert, which is starting to burn now. And historically, it never has. There hasn't been the fuel continuity that you needed to sustain fire activity in that region, but because of invasive grasses, now it's becoming more and more common. So this model gives us one way to come up with an answer without having that type of historical data. And this was an attempt by a former student of mine, Olivia Hoke, to use this modeling approach and measurements made at various times after fire in 3 different locations in the Western US, to use the model to look at how debris flow initiation thresholds should change over time. And she cast this in terms of a peak 15-minute rainfall intensity associated with a storm. You don't need to think about the 15-minute average at this point. Just think about the y-axis as it's a measure of rainfall intensity. And these gray bars here indicate what the modeled threshold would be. So it would take a 15-minute rainfall intensity, or what I'm going to call an I-15, of about 35 to 40 millimeters an hour to produce a debris flow at the Buzzard Fire in Western New Mexico in the first year after a fire, when the effects of that fire are kind of the most extreme, right? There's been very little, if any, vegetation recovery. Roughness is really low. Infiltration rates are really low because soil water repellency is high. All of these things lead to a relatively low threshold. To put that into perspective, the 1-year recurrence interval rainstorm is about 45 millimeters an hour. So this is less than a 1-year recurrence interval rainstorm is going to produce one of these extreme responses in this watershed that she was modeling. After 1 year of recovery, where you get some of that vegetation back, you get some increases in infiltration capacity and runoff, your debris flow threshold goes up to roughly the equivalent of a 5-year storm. And then after 3 years, it takes a 25-year storm to produce a debris flow. So you can see how rapidly your susceptibility changes and how quickly the landscape recovers. But in the first year, even though we tend to think of these debris flows as extreme responses, it's not really particularly extreme rainstorms that are causing them. It's actually rainstorms that you would expect every year or multiple times in a year. It varies from fire site to fire site. At the Pinal Fire in southern Arizona, again, looking at these same recovery metrics and how they affect hydrologic response, you get a big jump up from the threshold in year 1 to the threshold in year 2, where after year 1, it takes really a 10-year storm or more to produce a debris flow. But then your susceptibility doesn't really change over time. It kind of levels off. Same thing with the fish fire in Southern California. So there's site-specific responses that are associated with kind of the individual recovery of these different burn scars and what happened there. But this type of modeling framework helps us kind of start to tease that out and look at what's causing that and why we see variability from site to site in terms of recovery rates. One of the drawbacks to this type of an approach, though, is that I've kind of glossed over them so far in this kind of 30,000 foot overview. But in a burn scar, there's a mosaic of burn severity patterns. A fire doesn't uniformly affect an area. And in this modeling exercise, we only looked at watersheds that burned at moderate high severity. So in that sense, there were relatively uniform conditions within the watershed we were looking at. But if you really want to think about things at the scale of a fire, and you want to do them you want to look at watershed scale things within that, then we need to account in some way for spatial variability of the burn severity of the fire and how that affects the parameters that are going into the model. So here's a photo from this low burn severity area. You'll notice that there's still, so the fire did creep through here. You can see there's some ash here on the surface. But a lot of the canopy, some of the needles got charred, but a lot of the canopy is in place. So there's still interception capacity here. There's still relatively high roughness. There's pine needles, there's litter and duff and twigs and down logs all over the forest floor. In this moderate high severity area indicated here by the oranges and the reds, there's no canopy. It's a very low roughness surface. And the infiltration capacity in these two areas was also notably different. We were able to measure that difference. So it's challenging to account for all of that in a physics-based model. So our approach and the approach that others have taken is to go the more empirical route to assess debris flow likelihood at larger scales across watersheds with thousands of watersheds that you're interested in. And the way that folks have approached this problem in the past is to gather large data sets of historical observations where they go out to different watersheds and they install rain gauges. So they have estimates of, for each storm that occurs after the fire, what are the rainfall characteristics? And then they go back repeatedly and monitor responses to figure out in different watersheds that are burned at different severities and that have different terrain properties, what rainstorms produce debris flows and what rainstorms don't. And based on all of that data, they can train empirical models, in this case, a logistic regression, to predict things like the probability that a watershed will experience a debris flow. And they found that that's a function, not surprisingly, of terrain. Thinking about our dimensionless discharge, that's important there. And burn severity, one of the metrics that's common, difference normalized burn ratio, which is a satellite-derived metric. Some factor related to soil erodibility, which maybe gets in a roundabout way at this grain size. It's in the dimensionless discharge equation. And a rainfall intensity, peak rainfall intensity of the storm averaged over 15 minutes. That these variables do a pretty good job of predicting debris flow likelihood. So what we wanted to do was expand this data set of observations that to this point has been made primarily in Southern California. At least all of the data that went into this currently used model that's used to assess debris flow likelihood throughout the Western US by the USGS. That data used to train this model was all collected in Southern California. We wanted to go see how things might change or be the same if we use a data set from Arizona and New Mexico. So now that we've amassed a sufficient amount of data, we kind of went through and played that game, but I want to show you briefly how we collected the data. I kind of described it a little bit, but one of the things that we do to constrain when debris flows happen is that we'll install pressure transducers into channels. So these are small instruments about the size, a little bit bigger than the size of my finger. We drill a hole into the bedrock, insert the pressure transducer in that hole, and then as flows go over that pressure transducer, it records changes in pressure. And we can actually tell based on the time series of that pressure when a flood happened or when a debris flow happened. And we can go out and field verify that too by looking at the morphology of the deposits that these different flows create. But that gives us a precise timing, even within the rainstorm, of when a debris flow passed by a given point. And then we can install rain gauges also at these locations and use that to connect when a specific rainfall intensity with the timing of those debris flows. And of course, each watershed that we monitor is its own kind of unique natural experiment because each watershed has different burn severity characteristics, different terrain attributes that may make it more or less susceptible to fire or to debris flows. So here's an example of some of this data. This is the Tadpole Fire in New Mexico. Here's a channel a little bit downstream of this. We had a pressure transducer installed. Here's the recording from the pressure transducer as a function of time. And you can see that there's a large spike in pressure here, which we associate with a debris flow. And that debris flow occurred at roughly 15:39 on July 18. And at that time, the 15-minute average rainfall intensity was roughly 50 millimeters an hour. You can see here the difference between the 1 minute or near instantaneous rainfall intensity in the dashed line, and then this 15-minute average intensity in the black line. One thing I want to point out is just that the hydrologic response here of these watersheds, like I mentioned before, is extremely rapid. So it doesn't take much rainfall before you really kick things off. And there's a pretty nice correlation between the rolling 15-minute average of the rainfall intensity, which is I-15, and the runoff response. And this is typical that these two are fairly well correlated, which is why I-15 tends to be the rainfall variable that's used in empirical models to predict likelihoods of post-fire debris flows, because the initiation of those flows is highly linked through things like dimensionless discharge to runoff magnitude, and runoff magnitude in these small burned low order watersheds is highly correlated with rainfall intensity over a 15-minute time period. So that's one way in which these observations kind of confirm and can help us develop these empirical models. Different site, slightly different response, but actually surprisingly similar rainfall intensity that generated a debris flow here. Another fire in New Mexico, I-15 to 55 millimeters an hour. Totally different fire, watershed with different terrain attributes. This is southern Arizona. Much higher rainfall intensities needed to produce debris flows in this watershed, 80 and 110 millimeters an hour. Okay, so we take all this information, throw it into our empirical model, and we look to train a model. For starters, it's just the exact same form as what was done by others. And we got a pretty good, in my opinion, a pretty good model result. A true positive rate for predicting when debris flows should happen of about 0.88 and a false positive rate of 0.11. If we apply the existing model trained in Southern California to our Arizona data set, we get a 30% false positive rate, which means we're often predicting debris flows in watersheds that don't produce debris flows, which isn't great. And a fairly low threat score if you're familiar with that metric. So what this tells me is that taking this existing model trained in Southern California and transporting it to Arizona doesn't seem to work well for some reason, but these same factors are still related to debris flow susceptibility. But we just need to retrain the model and tweak the coefficients. And here's the difference that you might get in terms of the debris flow likelihood that you're going to produce, applying the existing model versus applying this preliminary updated model. You see much lower in general debris flow likelihood being predicted for a 1-year recurrence interval stored. So these models would make a difference. Why is this the case? Well, I'll give you one really simple explanation, which is that in the transverse ranges of Southern California, where this model was applied, or where this initial model was trained, the landscape is really, really steep. And in the absence of fire, it's vegetation itself that actually holds up a lot of sediment on the hill slopes. The sediment essentially gets dammed behind the stems of the vegetation. And when that vegetation is removed during the fire, you essentially get dry avalanches of sediment down into the channel. And that loads these channels with really fine, what we call dry ravel deposits, really fine, cohesionless hill slope material that's now in the channel and is very easily erodible. So think about that D50 in the dimensionless discharge equation. This is a very low D50 compared to what we see in other regions of the Western US that don't experience this type of dry ravel. So it's site-specific processes like this that I think kind of come back into why the coefficients in these empirical models need to be different. But more work is certainly need to be done to fully understand this trend that we're seeing. Okay, so I'm going to breeze through this next section because I really want to at least show you, talk about this last question, which I think is really interesting. How far are these debris flows going to go and what are they going to impact? But we also want to know at least something, we need to know something about debris flow volume to understand impacts, because large debris flows may inundate large areas and have greater impacts on infrastructure, whereas small debris flows, maybe they inundate a Forest Service road, but they don't really do too much. So we need to know this is going to be a 50 cubic meter event or a 50,000 cubic meter event, right? How much sediment is going to be mobilized by these flows? And we play the same game. We go out to these different sites that have different terrain properties, that experience different rainstorms, that have experienced different fire severities. And whenever we can, we estimate the volume of sediment mobilized by debris flows. And you'll see here some of the different types of debris flow deposits that we might see. And we'll estimate the volume of all of these whenever we get them for these different watersheds. We can use that data to train an empirical model. And this is the model introduced by Gardner and others that the USGS currently uses for hazard assessments in the Western US. It's based on a terrain property related to relief, which is the difference in elevation between the highest point on a watershed and the lowest point. It's related to the area in the watershed that's burned at moderate high severity. And again, importantly, this 15-minute rainfall intensity variable. When we look at our observations, this model doesn't do great. It vastly overpredicts the amount of sediment that's going to be mobilized by debris flows. This orange line is the 1-to-1 line. Our observations are the black dots. So we're off by probably an order, 1 to 2 orders of magnitude. But again, if we just retrain the model using the same characteristics, but tweak the coefficients, we can actually get a pretty good match. So it's not that that there's fundamentally different variables that are important here, but it's that there needs to be small adjustments to the model in order for it to really make sense. So again, look at kind of differences in the volume that you would assume would be produced. This is a fire that burned in southern Arizona using the data from Southern California in this Gartner model, and using a model trained on our Arizona data. Big differences in debris flow volumes being produced. And again, I think this comes back to dry gravel processes and sediment supply and things like that are different among the two regions. Okay, so a little bit about this last point here. One of the things that we've been working on and that I'm really excited about is coupling what output from atmospheric models that quantify precipitation intensity with these debris flow likelihood and volume models that can tell us where debris flows are likely to happen and how big they're going to be, to look at when we would expect we might get extreme downstream impacts, like what we saw in this case with Montecito that I talked about earlier after the Thomas fire. It was impacted by this fairly intense narrow cold frontal rain band, just even actually before the fire was contained. So we have this existing link between rainfall intensity, likelihood, and volume. And then the last piece of the puzzle that we need to fill in is, if we have a debris flow with a given volume, where's it going to go? So if we can fix this, if we can put in this last piece to the puzzle, then in theory, we could take output from an atmospheric weather model, in this case, West Wharf, and look at the 15-minute average rainfall intensity over each watershed in our region, as predicted by this atmospheric model. Throw that into the likelihood model to determine if a watershed is going to produce a debris flow, given that 15-minute rainfall intensity, how big it will be, and then we route that volume of debris downslope and see what it's going to impact. So we developed, one of my grad students led the study, Alex Gore, recently published a paper last year on this new model that does exactly this. It's kind of a semi-empirical routing model that, given a starting point and some volume of debris, tells you what areas downstream of that will be impacted. Here's an example of that model output. So it gives you estimates of peak flow depth. So you can see the parts of this alluvial fan and how variable flow depth would be over different parts of this fan, from more than 3 meters in channels to kind of less than half a meter in areas where it kind of goes over bank and spreads out. So we set up a West Wharf model. This was done in collaboration with Nina Oakley and others at Scripps, to essentially mimic a 24-hour lead time forecast for this event that produced these damaging debris flows at Montecito that occurred on January 8th to 9th, 2018. It was a 100-member ensemble that generated 5-minute precipitation output that we could use to compute 15-minute average rainfall intensity over each watershed. And we use that as input into the debris flow likelihood and volume models. And then we use that volume as input into this new debris flow runout model. And we can get something like this. Here's for ensemble member 64. There was a mean I-15 in the watersheds above Montecito of 67 millimeters per hour. That results in a debris flow in each of these watersheds. It actually results in fairly high volume debris flows that lead to large downstream flow depths and that spread out over the fan. We could look at ensemble member 33, a much lower mean rainfall intensity over this area, and it produces only debris flows in 3 of these watersheds, and they're much smaller, so they don't spread out as much. They don't impact nearly as much area. And we can combine all of this, the results from these 100 ensemble members, into a map, a single map, to produce the likelihood of inundation. So all these areas that you see in dark red are areas that are inundated essentially by as a result of every single ensemble member. So they're always inundated. So we would have high confidence that those areas probably would be inundated in response to this forecasted storm. Whereas these areas in the light blue, we may have really low confidence that they might be inundated, but it's still possible. The model is predicting that 1 to 2% of the time, these light blue areas might get impacted. So we can look at what atmospheric scientists sometimes call a reliability curve. Maybe some of you are more familiar with this than I am. But it shows the mean predicted probability of inundations. This is the model on the x-axis versus the relative frequency of inundation on the y-axis. Essentially, what it says is that, I mean, what you want is that, well, the way to interpret this is this 0.2 is roughly, these are all of the areas where the model says there's a 20% chance of inundation. And if you go and you actually look at those areas where the model says there should be 20% chance of being inundated in all of these green locations. So look at all those green locations. How many of those green locations were actually inundated? Well, 35% of those areas were inundated. So we're under predicting, essentially. We're saying there's a low likelihood of areas being inundated, but they're actually being inundated at a greater frequency. So the fact that this blue curve lies above the 1-to-1 curve is equivalent to a dry bias in an atmospheric model, that we're under predicting inundation extent. The black line here is the actual observed inundation extent on top of our probability map. You can see areas like this here, where there was this location where debris flow evolved out of a main channel and scooted across the alluvial fan over here. And we have that modeled as being a 1 to 2% probability of inundation. So you can kind of see some of that here. We're in general under predicting. But the actual, what I think is important and a nice result is that the observation is contained in a sense within the envelope of the ensemble. So that's nice. One thing interesting for future work, this model is extremely sensitive to volume. Here's a sensitivity index. Higher sensitivity index means the model output is most sensitive to that variable. It varies from 0 to 1. If we put in a dummy variable, what's the influence of some random number that has no influence on the model result? Its sensitivity index is about 0.05. The two other parameters in the model barely come out as being significant in terms of affecting model output. The volume is the big thing, and we have really poor constraints on volume. Even though this updated Arizona, New Mexico model that we're excited about to use in Arizona and New Mexico, there's an order of magnitude of scatter on either side of this curve here. So there's a lot of bang for your buck in improving these volume models, is what we found out from this study, because this runout model that we'd often like to use to predict downstream hazards is really sensitive to volume, and we have poor constraints on volume. So that's low-hanging fruit for future improvement. All right, so these are a couple of key takeaways. I guess hopefully I've impressed upon you. I think the extent to which these extreme events are linked with short duration, high intensity rainfall, though not necessarily particularly extreme rainfall, these burned watersheds in the Western US are pretty susceptible to debris flows because they can be generated by rainstorms with less than a 1-year recurrence interval. And this framework that I mentioned, won't read through all these, but I will mention that I think this framework that I mentioned down here is ultimately really useful for looking at future climate scenarios and assessing things even in a pre-fire context too. It doesn't need to be applied only in a post-fire context. We can simulate a synthetic burn severity map and run through and produce these types of maps. And we don't need necessarily an atmospheric model that's associated with a forecast. We could drive this type of analysis with climatology of intense precipitation or some anticipated distribution of I-15s in the future. So it doesn't have to just be used as an immediate post-fire response tool. It could be used in other contexts too. And I think actually that's maybe right now where it's most applicable. So that, I'm happy to take any questions as we have time. Thanks.
Hi, thank you. my poor students in hydro are gonna get a bonus spark opportunity for watching your seminar. The question I have is, beautiful work on looking at, you know, the magnitude of the rainfall and the intensity following the fire. Obviously, not all fires are created equal. Really clear on the mapping out of different intensities and the influence on, you know, surface roughness and overland flow and so forth. The question I have is, how much control do you have on antecedent soil moisture conditions? Does that data exist? Is that also low hanging fruit in an area and teasing out and maybe refining coefficients and determining the impact of the subsequent rainfall?
Yeah, so into what past studies have found, and there's a USGS scientist by the name of Jason Keene who has a really nice paper on this, 2011 paper about something like in situ measurements of post-fire debris flows in Southern California, where they have really good soil moisture data, soil moisture, rainfall, runoff response in small watersheds.
Pre-fire?
Post-fire. Because your question was about like how much does like antecedent soil moisture affect the debris flow response?
Because
after
the
fire?
surface impact of a fire could appear the same, but the soil surface below or impact on the depth of the heat penetration.
Oh, I see,
therefore
I see.
Killing off the rooting zone, affecting the microbiome.
Gotcha, yes, yeah, okay. No, so that's an interesting question, and one that I think I don't have a good answer to, and because you're getting at then what's how might a moderate burn severity fire in location A be different than a moderate burn severity fire in location B, because during the fire behavior was different because soil moisture was different, or et cetera.
The surface looks equally impacted, but what happened at the soil down was actually quite distinct. Because of antecedent moisture.
Yeah, and so the short answer is this is very complicated, and it's one reason why I think it's when we apply these physics-based models, we can kind of account for that because we're actually making measurements in these different areas. So we're theoretically picking up on, we're not just using like moderate severity as a proxy for something, but we're actually going to that area and making the measurements. And if it's different in one area, moderate severity in site A, different than moderate severity in site B, we should pick up on that with our measurements. But it's a real challenge, and it's one reason why why I think there is a lot of slop in all of this stuff and a lot of uncertainty. For a number of reasons. So I don't have a good answer other than I agree it's important, and a lot more studies need to be done to try to constrain what factors are causing the site-to-site variability and things you're talking about.
And it all hung up on the same plot with the discharge and slope for the hydrological mode. Why is the discharge smaller at a larger slope? So it looks like you have this negative trend there, right? You had it on your summary stuff. Yeah, like here or here.
Yes, so this isn't that discharge is smaller, it's that less discharge is required to produce a debris flow on a higher slope.
Oh, I see. That dimensional discharge is not the discharge. It's, what is it? It's what's required to cause the.
It's the discharge. Dimensionless discharge is the discharge divided by some density 50 particle size discharge you need to produce a debris flow given a particular slope. So at a steep slope, you need less dimensionless discharge to transition from a flood to a debris flow.
Gotcha.
Just because your landscape steeper, it's easier to pick up the sediment. Yeah.
Thank you.
Really great talk. So I have two questions about your third part of your talk. So first is, do you plan to implement your forecast model over a larger scale, spatial scale, than just the Southern California?
Yeah, I think this is one reason why we're trying to understand how to generalize these different likelihood and volume models, because we would ideally want to be able to use this type of framework anywhere in the Western US. So that's kind of what we're moving towards as we try to generalize these different empirical models that are involved in the process. Yeah.
Okay. So my second question would be, so you use I-15 rainfall for this model. Do you think that would lose some information about, because I imagine you would have instantaneous rainstorm time series, including intensity, the frequency, like the time series of the rainstorm. Would you think that would lose some information in those instantaneous rainstorm, that maybe you use that could capture the timing of the debris flow?
Yeah, for sure. So here we're not looking at timing at all. We're just looking at like
Downstream hazard.
downstream effect, yeah, downstream hazard. But certainly whenever you condense a time series down into a single metric to kind of characterize it, then you lose information. And so we're basing our choice of I-15 on just which if you are going to take a rainfall time series and condense it down into one metric to try to predict these quantities that we need, which one does the best? And we found I-15 generally makes the most sense. But certainly I think more work can be done, especially in terms of debris flow volume and seeing whether or not incorporating more of that variability in rainfall intensity within the rainstorm might yield better predictions of debris flow volume rather than just using this 15-minute average intensity.
Thank you.
So I think the one hand going up here, yeah.
Oh, thanks. I am so struck by your students' work, and it shows that huge jump up in resilience between year 1 and year 2 in that 4-year study.
Yeah.
And I want to know all about like what processes explain that huge change.
Yeah.
I have all kinds of hypotheses in my mind, but my question, I guess, is a big part of it that debris flows seem almost inevitable in the first year, and so you're removing a lot of fine material in that first year, or is it all like plants coming out?
No, that's a great question. And so Olivia has a wonderful figure in her paper that gets at exactly that question of essentially partitioning out. Like here, there's an increase from 30 to 120 in the threshold over year 1. What percentage of that is associated with vegetation recovery? What percentage is associated with soil recovery and changes in infiltration? What percentage of that is associated with an increase in the D50 grain size? Because as you say, you're preferentially eroding the fine material. And so with the model, we're able to partition that out. And so she did that for each of these cases, and it's not surprisingly different at each site. So at the Pinal fire, this large jump is associated with a big, mostly an increase in the median grain size from year 1 to year 2 because of preferential erosion of the fines. At the Buzzard fire, this increase from year 1 to year 2 and year 2 to year 3 is almost all associated with increases in infiltration capacity. So it's soil recovery, and the grain size, the D50 didn't change. And why is that? Here's that site right here. It's because the debris flows were eroding through really thick old colluvial deposits that there was just kind of an unlimited amount of the same stuff. So the D50 didn't change. Yeah. So yeah, great question.
Cool.
Yeah.
I found your talk really interesting. Thank you. I was wondering if you could go back to the beginning. I think you were showing short-term and long-term erosion rates, and how those kind of average out, or I guess with the fire erosion. So I was really looking at get a handle on the time scale there. So does this mean that if you look deeper in the geological record, that fire, like the frequency of fires has been important for long-term erosion rates? I mean, so we just happen to be living through a period of time where it seems like fire frequency is increasing, but in the geological past, is it abnormal now or not? I mean, are people looking at this like charcoal records or near term sort of?
Yeah. I mean, so I think the basic answer is I would argue that in landscapes like this, fire has always been an important agent or facilitator of geomorphic work. And that's, I think, what this study reflects. But I also think we're moving into a time period now where we have kind of anomalously high fire activity as a result of climate and land management and a number of things. So I think that it will become an even more important, it's already, I think the past shows it's an important geomorphic agent. And I think it'll be even more important in the next 100 years as all of these things shake out.
Yeah. The only question about the repellency of, so is it due to the oil for the plants? Is it the ash, like in blocking the pore space? Like what's the You expect
Yeah.
to see differences with areas of different kinds of vegetation or?
Yeah, you would, and it is associated with volatilization of a lot of the kind of waxy organic compounds in the canopy and litter. And as a result of that, sometimes you actually get really large decreases in water repellency after a fire in areas that are naturally water repellent, like chaparral that dumps a bunch of litter that has some of those compounds in it. It produces naturally water repellent soil, so sometimes after fires in chaparral, you see decreases in water repellency, and then as the organics come back in the soil, you get increases over time. So it's the opposite of what most people think of. So yeah, it does vary by ecosystem, and it's kind of modulated by fire severity.
Thank you very much. I appreciate it.
All right, well, let's thank Luke one last time.